Let's talk about finding the derivative of a function using the chain rule. Now the chain rule is a shortcut, like so many of our shortcut rules that we use to find the derivatives of functions, that allows us to find the derivative of a composition of functions. So just a quick review. Let's say I had a function f of x equals x to the fifth, and let's say we had another function g of x, which was 3x squared minus 7x. Okay? If I wanted a composition of functions, in other words, if I wanted f of g of x, what that means is I put g of x in as the input for my f of x function, so that would become 3x squared minus 7x, all raised to the fifth. And I can call that a new function. Let's call that h of x. All right, just for fun. So I have h of x is equal to the quantity 3x squared minus 7x, all raised to the fifth. Let's say I want to take the derivative of h of x. Well, we already have the tools to do that. I could simply expand this out, Pascal's triangle, expand that out, get a really long polynomial, and then just use the power rule for each term. I could do that. Or I could write 3x squared minus 7x times itself 5 times and do the product rule, which would take a little less time. Or we could use the chain rule, which we discovered in class by using the product rule. So if you haven't tried this already, pause the video, write out 3x squared minus 7x times itself 5 times and use the product rule. A prime times b times c times d times e plus b prime times a times c times d times e. You're getting the idea? Do that and see if you can discover the shortcut for the chain rule. All right, so let's say we have done this. What you discovered when you took the derivative using the product rule and combining like terms was that you had 5 terms and they were all identical. Each term had 4 3x squared minus 7x's. In other words, it was 3x squared minus 7x times itself 4 times, times the derivative of that. So this is what you get if you do the product rule with 5 terms. So if you look at this, you can see a cool pattern. And you realize, hey, really what I just did, a shortcut, rather than doing the product rule, is to think of this as a big power rule. So in other words, that's something raised to the fifth. So I did the power rule, 5 times that something to the fourth, then times the derivative of the inside. And that's what the chain rule is. The chain rule in words, the derivative of the outside function times the derivative of the inside function. That's it in words, okay? So you think of this function, the outside function is raised to the fifth. So here's the derivative of the outside, 5 times that to the fourth. The inside is my 3x squared minus 7x. The derivative of 3x squared minus 7x is 6x minus 7. So this is the derivative of the outside times the derivative of the inside. Okay? And kind of the formal way to write the chain rule is to embrace where we started, this composition of functions business. So the chain rule is if you take the derivative of a composition of functions, f of g of x, that derivative is the derivative of the outside times the derivative of the inside. Take a look at that for a moment and see if that makes sense to you. The derivative of the outside is your f prime of g of x times the derivative of the inside. That's the chain rule right there. Okay? Now we can combine that with all of our other rules. Our exponential functions shortcut rule. How to take the derivative of sine, cosine, tangent. We can even combine it with our product rules and our quotient rules. So the chain rule is going to be very, very useful. Let's do a few more examples. Let's say I had a trig function. Let's just say it was the sine of 5x minus 7. Okay? Hey, this is a chain rule situation because I have an outer function, which is the sine function, but instead of there just being an x there, there's another function there. There's a 5x minus 7. So to take the derivative of this, I'm going to do my chain rule. The derivative of the outside, well, the derivative of sine is cosine, times the derivative of the inside. Derivative of 5x minus 7 is 5. There's my derivative. Now, usually I would clean this up. That 5 is usually something that we would write as a coefficient. So this would be kind of the standard way to write that derivative. Isn't this kind of fun? Let's do an exponential function. Let's say y equals 2 to the 5x squared minus 7x plus 1. All right? So again, I know how to take the derivative of exponential functions. It's the natural log of the base times the exponential function as is. But now, look, this is my input, right? My input is not just an x, it's another function that we put in there. So the outside function is my exponential piece. My inside function is the exponent itself. So the derivative of this, I'm going to use Leibniz's notation, is the derivative of the outside, so that's the natural log of 2, times that whole shebang. Shebang, of course, is a technical math term. Just kidding. Okay, times the derivative of the inside, which is, and parentheses are essential here, 10x minus 7. And I hope you see why the parentheses are essential. It's this times this whole quantity. You know, there isn't a whole lot I can do to simplify that more nicely. More nicely? Anyway, that would be fine to leave it like that. Just make sure that that last parentheses is clear. All right? So we can also mix and match these things. Well, actually, before we mix and match, let's do, let's say g of x is the square root of, I don't know, I'm into 5s today. All right, not that big of a deal, okay? All right, well, we know we can rewrite this as 5x minus 1 to the 1/2. We've got an inside, we have an outside. The outside function is the square root function, or the raised to the 1/2. So that's going to be like a big power rule. So 1/2 times that to the negative 1/2, that stays the same, times the derivative of the inside, which of course is 5. Okay? And if I wanted to rewrite this, I'm going to bring that 5 with that 1/2. You could rewrite it as 5/2 times the quantity f, 5x minus 1 to the negative 1/2. Or if you prefer to write it without negative exponents, that 5 could be in the numerator. The denominator then would have the 2 and that positive fractional exponent. All right? Okay, so let's mix and match some of these. Let's say I had y equals let's say 3x squared plus 5x. I told you I was into 5s today. To the second times 2 to the 3x minus 5. Oh my gosh, 5s and 3s. What is it? Okay, so this is more complicated here. So you have to look for what the overarching rule is. I have something times something. I'm going to have to use my product rule. I have a function times a function. So my overarching rule here is the product rule. But in the process of doing my product rule, the chain rule is going to apply. So let's call this my A, this my B. Remember my product rule. Derivative of the first times the second as it is, plus the first as it is times the derivative of the second. Here I go. This might take a little room. Okay, so the derivative of the first, that's going to be a chain rule because I have a function inside of a function. So it's 2 times that whole thing to the 1. Of course, you don't have to put that 1. That's the derivative of the outside times the derivative of the inside, 6x plus 5. That's my A prime times B, so just times this as it is, plus, these can take a lot of room, this as it is, 3x squared plus 5x squared, times the derivative of this. That's a chain rule because I have a function inside of that function. So the derivative of the outside is the natural log of 2 times, shucks, I'm running out of room, 2 to the 3x minus 5 times the derivative of 3x minus 5, which is 3. Okay? Let me erase this so I can write that in one line, because that is not very satisfying. All right, so it's the natural log of the base times the exponential piece as it is times the derivative of that inside. Okay? You know, there's not a whole lot to do here either to simplify. If you wanted, you could do some factoring, right? You could factor out a common factor of 3x squared plus 5x. You could factor out a 2 to the 3x minus 5 and write your leftovers. Let's just do that for fun. Sometimes in scenarios like this, we actually factor. So let's see, they have a 3x squared plus 5x in common. They have a 2 to the 3x minus 5 in common. Big parentheses for all the leftovers from this first term. I have a 2 left over. That's gone. I have a 6x plus 5 left over. Plus, in the second term, let's see, I have a 3x squared plus 5x left over. I have a natural log of 2 left over. And I have a 3 left over. Not a whole lot I could do. I could distribute that and call that 12x plus 10. But, you know, there's just so far you're going to go. All right? So often, after we do a complicated derivative like this, we'll do some factoring to kind of chunk things together. All right. You can also have multiple chains together, like a chain in a chain. Let's do one of those, and then we'll call it a day. So let's say I had f of x equals the sine of the cosine of 1/2 x plus 5. This is going to be kooky. Okay, so let's look at this. This is clearly a chain rule because I've got an outside function and an inside function. But the inside function has another inside function. So you're going to be doing a couple of chains. So let's see how we think this is going to work. I'm still going to do my derivative of the outside times the derivative of the inside, and then I'm going to have times another derivative of the inside. So my outside function is sine. So the derivative of sine is cosine. The derivative of sine is cosine, cosine, cosine. Okay, there's the derivative of the outside times the derivative of the inside. Well, the derivative of cosine is negative sine, so this is all going to be times negative sine of that whole thing. But hold on, this has an inside. So it has to be then times the derivative of 1/2 x plus 5, which is 1/2, and you're good. Now, this is, believe it or not, one whole term. It's just a blob of things multiplied. So let's rewrite this so this looks a little better. Whenever you have a negative in the middle of a term, do not leave it there, because then it can look like a subtraction if you're not careful. Whenever you have just a constant multiplied in there, bring that up front so it looks like a coefficient. So I'm going to bring this, that's really a -1. -1 times 1/2, I'm going to call that a -1/2 as my coefficient. Then it's the cosine of 1/2 x plus 5, all times the sine of 1/2 x plus 5. And there you have the derivative. Okay? Just be careful too. There's no multiplication here. This is the sine of this thing. Sometimes people want to do a product rule. Well, there's no product here. You're taking the sine of something. Okay? It's not an algebraic function there. All right, I know I said that was my last one, but let's just do one more. Let's do, let's say I have y equals the tan squared of x cubed minus 2x. Actually, let's do the tan to the 5th. All right? Okay, before we dive in, let's refresh our memory about that notation. That notation really, as we recall, means that this whole quantity is raised to the 5th. It's that whole shebang raised to the 5th. So that's this times itself 5 times. So again, you could write them out 5 times, do the product rule, but let's not do that. Let's do instead our chain rule. So the derivative of the outside, well, the outside function now is that raised to the 5th. So it's going to be like a big power rule. So it's going to be 5 times that whole shebang to the 4th. That's the derivative of the outside. There's the derivative of the outside times the derivative of the inside. We're going to have another inside again. The derivative of tan is secant squared times the derivative of this inside, which is 3x squared minus 2. Don't forget parentheses. It's totally wrong if you forget parentheses there. Is there much to clean up? Not really. I think we're good, as is. That's the chain rule. I think they're kind of fun. You're going to be using it a lot. So just train your eye to look for the outside, look for the inside, and don't forget if you have multiple insides. And most importantly, have fun.